Welcome to another Explainer. I am so thrilled you're here because today we are stepping into the ultimate computer science workshop. We're going to break down exactly how humans write code and how computers actually understand it. Whether you're currently studying for your exams or you just want a crystal clear picture of what happens behind the screen, you are in exactly the right place. Let's get started.
Here is what we're looking at today. 1. High and low-level languages. 2. Translating code for computers. 3. The compiler versus interpreter debate. 4. A tour inside the IDE workshop. And 5. IDE benefits and drawbacks.
Section 1. High and low-level languages.
So, when you sit down to write a program, you basically have two main choices to bridge the gap between human thought and the computer's binary. On the left, we've got high-level languages. These are problem-oriented and written using English-like statements. That makes them completely machine-independent, or portable. You can write your code once and it'll run on totally different systems. Pretty handy, right? Then, on the right, we have low-level languages. Now, these get right down to the metal. They relate directly to the specific hardware architecture of the computer. So instead of nice English statements, you're literally writing in binary or using short memory codes called mnemonics. And because it's so specific, code written for one CPU just isn't going to work on another.
So why on earth would you choose one over the other? Well, it's all about trade-offs. High-level code is incredibly user-friendly. It's way easier to read, write, and debug. Plus, a single line of high-level code can actually perform multiple actions behind the scenes. But you lose that direct, granular control. If you really need to manipulate the hardware directly to maximize efficiency and squeeze every last drop of memory out of the system, you're going to need a low-level language. The catch? It's highly complex, very error-prone, and one line of low-level code equals exactly one single action.
Section 2. Translating code for computers. Okay, so once we write our code, especially if it's high-level, the computer honestly has absolutely no clue what it means. We need a mediator to translate it into machine code so the computer can actually execute it. Let's look at our first translator, the assembler. This one is used exclusively for low-level assembly languages. Remember those mnemonics we just talked about, like LDA for load or ADD for addition? Well, the computer can't read those either. The assembler swoops in like a direct dictionary, translating one assembly language statement into exactly one machine code instruction. It's a strict 1-to-1 ratio that spits out an executable file.
But what if you're writing in one of those nice, English-like high-level languages? Well, that brings us to the compiler. A compiler is actually really fascinating because it scans your entire high-level program all at once before running it. Think of it like translating a massive book and publishing it as a standalone executable file, which we call object code. But here's the kicker. If it detects even a single error during the scan, no publication for you. It absolutely will not produce the file. Instead, it hands you a full error report for the whole code, and you've got to go in and fix every single bug before you can run it independently.
Now, on the flip side of that, we have the interpreter, which is another translator for high-level languages. You can think of an interpreter kind of like a live translator at the United Nations. It works line by line. It reads a line, translates it, and executes the action immediately before it even looks at the next one. Because of this, it never actually produces an executable file. And crucially, if it hits a syntax error, it just stops dead at its tracks and outputs an error message right there on the spot.
Section 3. The compiler versus interpreter debate. If you're studying for an exam, listen up, because examiners absolutely love testing you on the differences between these high-level translators. So let's break it down. Under process, the compiler translates everything all at once, while the interpreter takes it line by line. For output, the compiler hands you a shiny new standalone executable file, whereas the interpreter doesn't give you any file at all. For error handling, the compiler makes you wait until the very end to get a full report, but the interpreter stops at the very first error it sees. And finally, execution. Once compiled, a program runs totally independently, but with an interpreter, you actually need that interpreter software installed on the machine every single time you want to run the code. So, the real secret here is knowing when to use which tool. Here's a brilliant tip straight from the exam mark schemes. Programmers almost always use interpreters while they're actively building and developing their code. Why? Because stopping immediately at errors makes line-by-line debugging so much easier. But once the program is absolutely perfect and ready to go, they switch over to a compiler. That way they can ship a blazing fast, standalone executable product for the end user. It's literally the best of both worlds.
Section 4. Inside the IDE workshop. So where does all this writing and debugging and translating actually take place? Let's step inside the ultimate developer's workshop, the IDE.
IDE stands for Integrated Development Environment, and it's essentially a suite of programs designed specifically to help programmers write, develop, and test software. Think of an IDE as your master coding workbench. It consolidates a text editor, your translators, and your debuggers into one single unified application, so you're not constantly switching between a dozen different software windows. Let's take a look at the specific tools you'll find inside.
First up, we have the code editor. This is your main canvas. It's the primary text editor window where all those high-level English-like statements are actually typed out, written, and edited by the programmer.
Next, we've got the built-in translator. Rather than forcing you to save your file and open up an entirely separate piece of software, the IDE has a compiler or interpreter right there inside it. Literally, with the click of a button, it seamlessly converts your high-level source code into the machine code that the computer can actually run.
And that brings us to one of the absolute most powerful tools in your arsenal, the debugger. The debugger is essentially your magnifying glass. It helps you track down and fix pesky logical errors. It lets you single-step through your code, line by line, or even set breakpoints. Breakpoints purposely pause the execution at a specific spot, so you can peek under the hood, examine the current values of your variables, and figure out exactly where things went wrong.
Now, let's look at how this builds into real-time help with error diagnostics. While you're typing your code out, this feature acts kind of like a super sophisticated spell check. It alerts you to syntax errors in real time, usually by underlining them in red, and it often even gives you a suggested correction before you even attempt to run the program. It's a real lifesaver. To make you even faster, IDEs feature auto-completion. As you start typing a command word, a reserved word, or maybe a variable name you created earlier, the IDE actually predicts what you're trying to say. It'll suggest the rest of the word in a little drop-down menu. This massively speeds up your workflow, and honestly, it prevents so many silly typos.
And finally, just to keep everything visually organized, we have Prettyprinting. This awesome feature automatically applies different colors and syntax highlighting to your command words, strings, and identifiers. It literally transforms a giant, intimidating wall of plain text into a highly readable, visually structured document. Section 5. IDE Benefits and Drawbacks.
Now, IDEs sound absolutely perfect, right? But like literally everything else in computer science, there is a trade-off you have to consider. Let's weigh the balance here. On the benefit side, IDEs give you incredibly high efficiency by consolidating all your tools into one spot. They drastically reduce syntax errors thanks to those real-time diagnostics, and features like Prettyprinting make your code highly readable and super easy to maintain. But on the drawback side, professional IDEs are packed with so many features that they present a really steep learning curve for beginners. It can be overwhelming. Plus, they are highly resource-intensive. They're going to chew up significantly more of your computer's RAM and CPU power compared to just using a simple text editor. And lastly, some IDEs are completely language-specific, meaning they might only support Python or only support Java, which obviously limits your flexibility. We have covered a tremendous amount of ground today, from the core differences between high and low-level languages, to the exact mechanics of assemblers, compilers, and interpreters, all the way down to the unified workbench of the IDE. So I want to leave you with this provocative thought. Based on everything you've learned from this explainer today, if you were sitting down right now to build your very first computer game, what specific combination of tools would you select to balance ease of development with ultimate end-user performance? Seriously, think about it. Thank you so much for hanging out with me in the workshop today. Keep exploring, and I'll catch you in the next explainer.